Now I'm going to walk through a couple of problems that would require multiple methods of calculating heat that we've done in this unit. So you might get a lot of numbers. You might get some that have calorimetry and a reaction, or calorimetry and a delta H formation, or stoichiometry and delta H formation. And there's a whole lot of things that can happen. So we got to use our problem solving skills. You really got to read the problem, break it down. What do you have numbers for? What equations can I use? Okay, so I would also print off your equation sheet and have that right next to you. So you could have, maybe I did a calorimetry problem. So I did a bomb calorimeter or a coffee cup calorimeter, and then I wanted to know the enthalpy of formation for something. So I can use Q equal MC delta T. I can find my delta H from that, right? We already did that. And then do the sum equation and solve for when I don't know. That's like example number 9. Or I could do a calorimetry problem and then a thermochemical equation. So something with stoichiometry. Remember, we did stoichiometry. You can do a mole ratio with energy, just like you do with moles. Or maybe I want to know the final temperature of a solution. So this would be like if I put something hot and something cold and I said, calculate TF. That's again, 2Q equals Q equations, and you got to solve for TF. Just remember that the metal and the water at the end are always at the same temperature. We tend to forget that. So I'm going to walk through these examples. Feel free to just look at the examples if you want to, but I am going to talk through them. I recommend trying them before having me walk through them. But again, that's up to you. So I'm going to start with this one. I got combustion of liquid nitromethane. So I'm reacting this. Increases the temperature of a bomb calorimeter. So I got a Q equals big C delta T equation. Given the balanced reaction below and the heat capacity of the bomb calorimeter is 1.99 kilojoules per degree Celsius. So that's big C. Determine delta HF for 1 mole of nitromethane. Well, anytime I've got big C, the only thing I can do is Q equals big C delta T. So I'm going to do that first. The Q of my calorimeter is big C delta T. So 1.99 kilojoules per degree Celsius. Temperature change, I said it changed the temperature by, so you don't even have to do subtraction, 8.78 degrees Celsius. So this is the amount of energy that that reaction gave off. Now, before I plug it into my delta H sum of with the formations, I have to do it to delta H per mole. Delta H is always per mole. So I have to divide it by the number of moles of stuff that I reacted. Okay. So I took my 1.505 grams of nitromethane and converted it to moles, 0.02467 moles. So this was the amount of energy given off by this many moles of nitromethane. So it's negative 708 kilojoules per mole of nitromethane. Now, to get it for the reaction, remember, if I write a delta H over here for the reaction, it has to be for the balanced equation. Notice there's 2 nitromethanes in this balanced equation. So I have to be like, okay, well, 1 mole of the reaction, that's like 1 of this thing, has 2 moles of nitromethane. So it's negative 1,416 kilojoules per mole. Like if I was to write delta H, I would write it right here. That's what it would say. It goes with this balanced equation. Okay, so now I can use my formation equation. That's the only one that uses delta HFs is the sum of minus the sum of the equation. So I plug in my negative 1416. That's the whole reaction. And then I look up the other ones, right? Products minus reactants. So 2 carbon dioxides, 3 waters, and 2, that's 0, it's pure element. Minus, I'm looking for this one. So 2 of these, so that's 2x. That's what I'm trying to solve for. And 3/2 of O2, again, oxygen standard state is 0. So I would solve for x and be like, okay, x is negative 114.2 kilojoules per mole. This is a thinker one. All right. Example number 10, what mass of natural gas, that's methane, must be burned to heat 20,000 cubic feet, about the volume of a 3-bedroom ranch style home with a basement. That's a lot of air. From 18 to 22 degrees Celsius. So like how much gas do I have to burn to actually heat up my house? That's what I'm wondering. 4 degrees, that's it. Assume that the specific heat of air is, what does that say? 10 joules per gram degree Celsius? I don't know, I wrote over it. Density of air is 1.22 grams per liter. You are going to need that. The natural gas is mainly methane, so we're just going to assume it's all methane. And that the furnace is 90% efficient. This is like an extra credit type problem here. Okay, there's a lot of parts to it. So first of all, what can I do? Well, I'm trying to heat up the air. I want to know how much gas to burn. I want to change the temperature just this much. Oh, this is a delta T, so I can do a Q equals MC delta T. So I'm going to do that first. Q equals MC delta T. Well, I want to change it 4 degrees. That's pretty easy. I told you the C for air is where, oh, it is 1.0 joules per gram degree Celsius. And the mass. How much air am I going to be heating up? So this is a giant conversion problem. I have how many cubic feet of air? How much does that weigh? All right, well, I'm gonna go, I do all these conversions. These are the only ones I know off the top of my head. From cubic feet to cubic inches. Remember, if you do a cubic conversion, you also cube the number. So there are 12 cubed cubic inches in a cubic foot. So my feet go away. Then I want to put it into centimeters cubed because I know there's 2.54 centimeters in an inch. So it would be 2.54 cubed centimeters in a cubic inch. I said that, oh, I got the density of air. No, I'm not there yet. I got to get all the way to liters so I can get to grams. So 1 cubic centimeter is the same thing as a milliliter. This is on your equation sheet, something you should kind of just know. These are exactly the same. All right, then there's 1,000 milliliters a liter. Then I can use the density. There's 1.22 grams per liter. So this is how many grams of air exist in this house. So that's my N. All right, so that number goes here. I need, the Q is, after you do all this math, 2,760,000 joules. That's how much energy I need to heat the air. So how much methane do I have to burn? Well, I need this much energy, and I'm going to do a chemical reaction, so I got to do stoichiometry, right? Now, I'm going to put this in kilojoules because this is in kilojoules, so that's what I did first. Now, remember, when we're doing stoichiometry with energy, instead of doing a mole to mole ratio, I can do a mole to energy ratio, and I can do it whichever way I need to get my stuff to cancel out. So if I'm starting with energy, well, I want to put energy on the bottom, so the kilojoules cancel out. So I put this value on bottom is for 1 mole of CH4 because it doesn't have a coefficient. And I want to know what mass of natural gas. So then you just go from moles to grams. So all I did was convert from this amount of energy, use my mole ratio with energy, and then convert to grams. So I need to burn 49.6 grams of methane in order to actually heat this house. Now, that's if it was 100% efficient. So after that, then I have to figure out, okay, well, how much do I have to burn if it's only 90% efficient? This is where this is more of an extra credit part comes in. And I didn't really do the whole calculation here. I just said, well, okay, if it's 90% efficient, I need this much energy. How much do I need if it's 90% efficient? So 90% of what is 2,600,000, and so I lost a zero there, 1,000 joules. Then I can solve for X, and then I can do the whole conversion again. I'm not going to do that because, like I said, that's more of an extra credit part. So finally, example number 11 is find the temperature between two different, or the temperature at the end when you put something hot and something cold, or you do a reaction or something like that. So this is a multi-step problem. So we go, what is the predicted final temperature? So TF, right? Of a solution made by adding 5 grams of solid sodium hydroxide to 25 grams of water. Now, this isn't putting something hot and something cold. This is dissolving. So remember, when I dissolve, my Q equals MC delta T. The mass is the mass of the stuff I dissolved in the water. So in this case, it's going to be 5 plus 25. So that's 30. That's going to be my N. All right. So I know I'm going to have to do a Q equals MC delta T. You can see it down here. My mass is going to be 30. Let's see. Let's keep reading the reaction. This, I'm just dissolving. And assume the specific heat is 4.02 joules per gram degree Celsius. So that's my C. Now, what do I do from there? Because I don't have a temperature change. I want to know what the final temperature is going to be. So I actually need to solve for this temperature change. So how much heat am I going to make when I dissolve 5 grams of stuff? I meant to put this into your note sheet. I don't know if I did on the new one or not, but I would have said that this reaction here, the delta H is negative 41.6 kilojoules per mole. Okay, so I have a balanced equation and I have a mass of stuff. I want to know how much heat. I'm going to do this like stoichiometry. I'm going to convert my grams into moles. That's what I did, moles. 1 mole of stuff dissolving gives up this much energy. So I would go like 1 mole to negative 41.6 kilojoules. So this is the amount of energy that's going to be released when 5 grams dissolves. All right. Now, again, this is negative, right? Delta H means it's exothermic. It's going to give off heat. This does actually happen in the lab. When we try to make sodium hydroxide dissolve in water, it gets really hot. So heat is released. So I know that the temperature is going to go up. Just kind of keep that in mind. So your final temperature should be higher than 22.5. Okay, this is the amount of energy released. So this is my Q value. Now I have my C value in 4.02 joules per gram degree Celsius. So I went ahead and converted this into joules. So 5.20 kilojoules is 5,200 joules. I dropped the negative because the heat is being released by the process and then absorbed by the solution. Again, you can just kind of figure out the negatives at the end. If you left the negative, it's not a big deal. You could have left the negative right here and then solved for TF the other way. It's fine. So anyway, this is the amount of energy that this solution is giving off in order to heat up. So I'd be like 5,200 joules equals 30 grams times 4.02, solve for delta T. So delta T is 43.1 degrees Celsius. Now, if you had kept the negative, this would be negative 43.1 degrees Celsius. But you should switch the sign because it's being given. Either way, I know the temperature is going up because the negative delta H means it's giving off heat. So it's got to heat up. All right, so the temperature's got to go up by 43.1 degrees Celsius. So I did my starting temperature plus 43.1 degrees Celsius. I got 65.6 degrees Celsius. So when I dissolved this stuff, it actually gets this hot, and that's pretty hot. So you need to be careful whenever you're making sodium hydroxide solution. So again, make sure your answer makes sense. If you ended up with a lower temperature, well, this is exothermic, so it should get hotter. Think about that before you do your final answer.